Hi everyone. Today we're going to talk about the overfitting problem in our convolutional network. But before we directly go to the problems, firstly, I think we should have an understanding of the convolutional network. Right? We don't want to use it as a black box without knowing what's going on inside. So do you have some do you know some what does the neural net actually learns each of the layer? What kind of feature does it learn? You have some idea? Yeah, please, if you have, please tell us if you have some ideas about what does neural net actually learns. For example, for internet or the very classical neural net works. How does it work?
My understanding is that, for example, in the layer one, beginning few layers, we try to detect the edges.
Yeah.
It's a very low-level details of the image.
Yes.
And then as the layers move further to the deeper layers, it starts to recognize some more complex patterns or objects within the image.
Yeah. For some the lower layers is always some very common or simple texture features like here. Here is here is a paper. It visualize the visualize result of each layer. What does each layer learn? Here from this paper. You can go into this paper. There's many details. Here I put some pictures. Here is they give you result on the ImageNet, which has 5 convolutional layers. We can see that this is the first 2 layer. We can see that for the first 2 layers, the network mainly learns about some some simple texture feature like this one. The first layer is some edges, and the second layer, here is the second layer. We can see it's mainly also have edges or conjunctions or some corners, right? This is the first 2 layer. But for the third layer, we can see is some more complex text feature like for this one. This is the mesh, and it begins to generate to learn some class-specific feature, for example. But it just began to, not really. Only this one, it began to learn some feature about the class. For example, this is the human feature of the human. And as the layer goes deeper, and it will become more and more class specific. This is the layer 4. We can see that this one mainly learns the feature of the face of the dog, right? But this one learns the feature of the legs of the bird. So as the layer becomes deeper and deeper, the feature will become more and more high level and class specific. Here's the last layer. The last layer we can see is more class specific. This is the face of dog. This is also, and all of them are objects. Each branch they belongs to the same object, only with different pose variations. So it's more and more class specific. Only one exception for this one. You can see that. Can you see the picture for this one? Actually, they don't have much in common, right? For this bunch of pictures. But the neural network somehow learns that they are similar. So after you can see the visualized result here. Actually, this network it doesn't learn the forehand subject of the image. It actually learns the background. You can see all these pictures, they have a similar background to the grass ground. Yeah, so this is why the neural network make a mistake. They learn the background instead of the foreground, the subject of the image. So they make some mistake. Yeah. So after
would you say that's a mistake? I mean, that classifier there, that particular filter there is learning grass in the background, right?
Yeah.
But it can be correlated with certain classes later in the soft lex layer.
Yeah. It in terms of our human vision, we won't notice that the background grass, right?
Mm-hmm.
But some. Yeah, you can also see that it's right because they also have the wall of the pictures, they have grass background. So to some extent it's right. But for human, we always notice the foreground of the image, the subject in the image, to classify an image, right? When we see this kind of images, we won't classify it to grass ground. But
so it's a secondary feature, right? You're basically inducing features that can help you learn a class because it's mutual information with the actual primary class, right? So grass is a feature that you would see for animals or for outdoor activities. You wouldn't see it within a building. You wouldn't see it in synthetic environments. So it's another type of feature that's being captured by within the data set for ImageNet. So that's a good point. It doesn't have to be correlated with a single class, but it can be correlated with multiple classes in such a way that it can help identify those classes and distinguish them from others. As long as there's some positive net information that can help you to learn a class, it can be helpful for feature induction.
Yeah, actually, yeah. It just the in humans is it make a mistake, but actually it doesn't seem correct thing. Just then a common feature appears in all these images.
Does anyone know how many layers does this particular network have? This is AlexNet or which one? I don't remember which.
For this one, they have 5 convolutional layers in total, and then 2 fully connected layers.
Okay, so this is still a feature layer. It's not the actual output layer, right? This is still useful.
Yeah. So that's our understanding of the neural network. In lower layers is about some local feature, and higher layers is more specific, class specific. And then let's go to our problem about overfitting. So when we train our neural network, how can we decide that our network is overfitting? Because we should find out that our network is overfitting, then we can prevent it, right? So first we have to find out. So how can we find out?
My understanding is we need to look at the performance on the training set versus the performance on the evaluation set.
Yeah.
Because the deviation is very large and the model fits very well on the training set, but not so well on the evaluation set. Then say it's overfitting.
Yeah, exactly.
Do you want to add? You have your hand up.
Yeah, so that's the direct way of identifying that it's overfitting. So it's give a good accuracy in the validation set, but not similar in the test set.
Yes.
That's
Yes. Here I give an example. The figure are from this blog. You can, if you want to see more detail, you go to this blog. Yeah. So overfitting. When we have training data set and test data set, right? When the network give a very perfect, very good result on the training set, and then when you test it, but the accuracy is not that high. Well, for example, in this example, after 280 epochs, we can see that the accuracy on the test data stop improve. It just doesn't change too much after this point, right? But the cost on the training loss is still keeps decreasing. So we after 218 epochs, the neural network begins to learn some very detailed information of the training data set, which cannot be generalized to the test data set. So the training loss still keeps going down, but the accuracy doesn't go up. As we can, yeah. If there's this kind of phenomenon, that means that it's very likely that your neural network is overfitting. And then after we find out our neural network is overfitting, how can we what should we do to prevent it?
Data augmentation.
Data augmentation, yeah. One technique is data augmentation. How can we do? What do we do to do data augmentation? To have some idea.
You shape the image so that the foreground is like displays, so you rotate it.
Yeah.
Other combinations.
Yes.
You
So you
zoom out and try to enlarge or decrease the size of the image. So, like for example, the size of the feature got decreased and then it falls into your filter.
Yeah. So it's based on your existing data set. You do some transformation or crop or add noise to your existing data set. It will enlarge your data set, right? Any other techniques to prevent overfitting?
One technique that we discussed on the last lab, that is dropping out neighbors randomly.
Yeah, dropping out, another technique. Yeah, it's primary task of drop out is to prevent overfitting, right? And it actually works very well. And we have 2 techniques already. So do you have any other techniques about how to prevent overfitting?
Yeah, you can also use an ensemble. Like let's say if you are trying to do prediction, you can use a combination of models. By stacking them together, you use the variance of your overall prediction result.
Yeah. Is it normal? Normal, you mean? Can you be more specific?
Like so let's say you're doing a prediction task and you are currently using like a neural network alone. Yeah. So instead of like using the output of neural network alone, you can take like let's say average of the prediction of a neural network with the average combined with the output of let's say SVM or KNN. Yeah. And then by taking the average of those results, you get a more stable prediction. Yeah.
By using other
models in combination with your neural network.
Okay.
Let's also be clear about it. Your neural network is actually being ensembled anyways, right?
Yeah.
Because the neural network is a big ensemble. It's a exponential number of models that are all being trained together, and dropout is helping to generalize that even more. So I referred you to the Goodfellow book that has a pretty good mathematical explanation why dropout is so effective for training and battling overfitting in neural networks. But the general idea that Joe is pointing out is true. Like if you learn it from our typical machine learning class, not deep learning class, you combat overfitting by ensembling, by adding lots of different models that have different perspective on the problem. They can use different types of learning, so some could be linear classifiers like SVMs or linear regression. Some can be conditional classifiers like decision trees and other things like that. Some can be, memorizing the data set like KNN that typically does that. It doesn't do any learning. It just does distance evaluation between a test and a training instance. You can ensemble them all together. The key thing about ensembling is, again, you need to have models with very different perspectives, right? So one thing you may have heard about is random forest, right? Random forest does this partially through feature projection. Are you guys all familiar with what feature projection is? Okay, so I'll just illustrate. Let's say you have 100 features that you think are correlated to the task. Okay, feature projection just means I'm going to take a subset of them and give it to a particular learner. Okay, let's say I want to make 10 decision trees out of this data set. Okay, so what I do is I give the first one features 1 through 90. I leave out features 91 through 100. I give the second decision tree features 11 through 100. I leave out the first 10. Okay, so all of them are somewhat like different learners in the classroom who've gone to different lectures. They don't have all the information about all the lectures. So they have a slightly different mental model of what it means to do well on the final test. Okay, so they're going to study only their parts. And when you ensemble them, you're getting opinions from different students who have gone to different lectures, for example. So that's what we call by feature projection. It means you don't provide every piece of information to all the learners. Okay? And that also helps to speed things up because, of course, if you have less features, then the learner doesn't take so long to learn. So in random forest, for example, you tend to take something like the square root of the number of features. And you have a square root of number of features as the number of learners too. Okay, so you do that to create a very diverse set of individual learners who are learning the target class. Okay? This is why also in certain cases, when you hear about teams making decisions, it's a very different aspect from machine learning or deep learning. You hear about diversity of the teams, right? You want a diverse team to have different perspectives and viewpoints, and that's exactly the same idea, okay? So when we talk about diversity in ensembling, that's one way. Okay. Joel also mentioned regularization, right? So you guys know what regularization is? I think it's going to be covered more in subsequent lectures, but it doesn't hurt to talk about it now. Do you want to say?
Yeah, so regularization is the concept of handling the complexity of the parameters, especially to avoid overfitting.
Yeah.
So how do you deal with complexity of the parameters? What do we mean by that? Anyone interested to share?
So basically, we analyze the norms of the like in neural networks, and we have W as our learn parameters. And one simple normalization like T some lambda, which is arbitrary parameters, times the norm of W. We include it into our loss.
Like no, it's overly complex. The loss function.
Right. Do you know what that translates to, though? Do you know why that's important? Okay, let me try to illustrate this on the board for you. And I think that'll be a little bit easier to think about it. Okay, let's say we're learning a linear function, okay? And we have some points. Okay, so there's a linear trend here, but there's some noise to it, right? So when you have a complex model like a neural network, it's very easy to fit exactly those dots, right? Because you have enough parameters to do so. So your W could in fact go something like this. Right? That's perfectly fine because it'll get zero error on your training data. Okay, but if you look at the parameters of W, the coefficients for creating this polynomial would be pretty complex, right? So we all recognize there's probably a linear trend here, right? So we want a polynomial that's pretty simple, right? Either something that's a straight line, or has at most, a quadratic component to it, right? So when we regularize, we're basically saying we don't want the parameters to be overly complex, right? Because our coefficients, let's say we're learning a polynomial, it's going to be x plus x squared plus x cubed, right? And so we have all of these different parameters. Let me not use lambda. Use W. Right? You usually use W with theta here, right? So you have theta 3, W2 plus the intercept, right? So intercept is 0, right? So what we want are small numbers for these W's, right? Because they're going to induce a very gentle curve or line, right? When we have high values of them, they'll be very squiggly, right? They'll be all over the place. So you might be asking yourself, well, the data could actually be highly dimensional, right? And it could be that the case that you want W's that are very big, okay? But that's usually not the case. And the problem is that when you think about your signal and your noise together, okay, then it becomes clear why you want smooth lines, okay? Because let's imagine this is our actual trend, okay? And let me say, let's just resample the data, get some new data points, okay? So if they obey this trend, the new data points might be like this, right? So it's going to generate a different polynomial, right? If I have very small weights here, right, my smooth line is still going to match this data set fairly well, this new data set, this test data set, if you will, right? But if I have high coefficients here, it's not going to match at all, right? Because, you know, if I were to draw the line that fits this one, it would be something like this, right? Okay. So the important thing about regularization is it doesn't help to fit the data, okay? It helps you to not fit the noise. Okay? That's the key aspect of regularization. We want to combat noise because sometimes our data sets are not clean. Sometimes the sensor that we measure the data is not clean. Sometimes there's artificial artifacts like your camera or your imaging equipment or your sensor doesn't capture things correctly. Okay, so it's not so much that regularization helps you fit the data. It doesn't. It helps you combat the noise because the noise, once you resample, will give you completely different data points. Okay, and if you get a training error of 0, that means of course you're fitting everything, right? You're fitting both the signal and the noise, right? And you don't want to fit the noise because that's not generalizable, right? So this is why we need smooth coefficients. And when we do regularization, typically we're putting some constraints on all these values, right? So it means, for example, I want the sum of all the W to be within some cost, or I want the square of all of these to be within some cost. Okay, so that's L1 and L2 normalization. That's all it is. Okay, are we all clear about that? Okay, so try to remember that why regularization is important. Okay, the regularization is important to combat overfitting the noise. Okay, and not to help you fit the signal at all. It's not its purpose.
Okay, let's continue. Here I conclude some techniques for how to prevent overfitting. The first one is early stop. Early stop means that when you observe that your the accuracy on your validation, we have validation data set and the training data set. When the accuracy on your validation data set, it doesn't improve, but the training losses still goes down. But at this moment, you just stop your training. Yeah, this is called early stop. But this one is not, has some drawback because you have to also check your loss function and the accuracy very frequently to choose the right time to stop. And the second one is to increase the size of your training data data so that your network can learn more general information. But for this one, the larger data set is not always available, right? So I have to do data augmentation, just mentioned. Data augmentation can also, there are mainly two ways to do data augmentation. The first one is based on your existing data set, to add noise to your data set, or cropping the images in your data set, or do some other transformation like flipping or rotating. For us, another method is to generate your data set, to enlarge your data set. Use some generative model like VAE or GN. You use your existing data set to train this VAE or GN, and then you can just sampling from normal distribution or from noise to generate more samples for your training. That's for data augmentation. Yeah. For more, there are also other techniques. If you are interested, you can go to this paper to find more details. There are also other details based on the feature space to how to based on our from here we are based on our data space to enlarge our data set. You can also enlarge your data set based on your feature space. Yeah, for more details, you can go to this paper. The third way is regularization. The commonly used one is L2 long. Here you can how to implement this one is to add another L2 norm to your loss functions. Yeah. For example, for this one, you have a cross entropy, and you add another regularizer to your loss function, which will give a penalty to the weights of your network. So to enforce that the weight to be sparse. Yeah, but here the thing is how we choose the contribution of this term, the lambda, the value of lambda. This is actually a very general problem, because not only in this case, for other cases, when we train our network, we always combine different loss function into our objective function, right? Our objective function always have different loss functions, not only one. How to decide their contribution of each one? It's a similar question. How to control this, the lambda or the value of lambda? You have some experience of how to choose this hyperparameter?
So I guess you try different value and you find if lambda is too small, and then there will be, it will smooth out your model very much, or too much, that you have a very poor training set performance.
Yeah, but you have to visualize something, right? Visualize how can you judge that it's too small or it's too also for other cases, for example, I have two loss. My objective function is two loss, L1 and L2. Or I combine them together, and there's a lambda between them. How to tune this lambda is also a very general problem when we're tuning.
But what I mean is, can we just choose some lambda 1, lambda 2? So lambda 1, we use lambda 1 for the training set, and then we see the training set result, right, like this. And then we choose another lambda 2, and then we see the training set result. So
which is better, and then we choose that one. Firstly, the range may be large. The range different lambda may be large, and then we can specify some range, and then the step between them becomes smaller and smaller, and choose the better lambda value. Right? But how about for other cases that we have different? For example, I have two loss, loss 1 and loss 2. We have a lambda between them. Yeah. This kind of.
Do you guys have any input?
Have some idea about how to decide the contribution of each loss in your objective function?
So Alicia, yeah, go ahead.
I just randomly
Uh,
I think like I don't know whether there's a.
I mean, if you're really lazy, I guess you're talking about tuning the parameters of the regularization term, right? I suppose if you're really lazy, you can do a grid search and then there's all possible parameters.
But you still have to train.
You still have to train each one, yeah.
have to train, but yeah, for me, I also I don't have a very good solution. For me, I just visualize what the for example, I have loss 1 and loss 2. I'll visualize loss 1 and loss 2, plot them, and observe that if one is decreased, but another one just if another one is keep constant or just goes down a little, that means that your loss 1 is dominating, right? That means the contribution of the loss 1 is a bit large. So I just decrease it a little and then train again. Yeah, that's my solution. Yeah. So I just plot them out separately and see if whether there is a laws which dominate is dominating.
And then you
Sorry.
wouldn't you be confused like which term is dominating the most? And then if that gives you some information.
Yeah, so Li Chen's way is the empirical way, which is, I guess, what most data scientists do, right? We don't solve the math. We have lots of compute power, so we just throw it at the computer to figure it out. You're doing two different separate line searches, right? You're saying, I hold lambda1 fixed and I vary lambda2. I plot that. And then I can also do another plot where I hold lambda1 fixed and vary lambda2, right? Did I say it that way already?
Lambda1 is a function of lambda2.
Yeah, they are related to each other.
So it's actually only just one.
Yeah, you can grade it so it's only a single parameter, right? So many times if you're composing two loss functions, you do lambda1 times the first loss function and 1 minus lambda1 for the other loss function. So there's only one tuning parameter. And I suggest that you do that for all cases where you're trying to combine two things. It's easier. But even then, within each of the loss functions, sometimes there's other parameters to fiddle with, right? So doing two separate line searches might be good. In fact, a lot of optimizers do that. They'll say, hold everything constant, vary one thing, right? Optimize that one parameter. And then when I've got the right parameter there, freeze it, and then modify one of the other parameters, right? So if you see like sampling approaches that you might see in Bayesian techniques, they also do this, right? They hold everything constant, sample something, then get a new sample, and then use that to estimate a new model, and then resample using a different parameter. So those are all line search techniques to avoid doing the entire grid search, right? Grid search means you try every parameter, which is very, very exhausting. Well, not to you, but to the computer. And to SOC's electricity bills, if you're plugged in here. Yeah. Do you know how much our electricity costs per month? Millions of dollars. I'm not kidding. Yeah. Okay. Home center, but also, all the laptops, all the charging, everything, all the racks. So, GPUs, they take a lot of electricity, but what's more is like we have a lot of powered racks in SOC that aren't fully utilized. So a lot of research machines are not fully utilized. So they're just spinning and wasting electricity. So good to keep your systems really busy. Go to your servers, make them happy by giving them lots of workload. Okay, generate lots more work for our AC system to cool the racks down. Thank you very much.
And then the fourth method is the job out. We mentioned just now. We also mentioned in our last group meeting, right? For the job out, the details of job out is in this paper. If you are interested, I just give some intuition behind job out. The inspiration behind job out is that combining smaller networks together or generally has a bad performance than one large network. So this is the inspiration behind the job out. You can see that this is standard network, doesn't use job out. This is the network after using it. In job during the training, it means in job out there, it means that each neuron will present with a probability of P, and during test, it will always present, but its weight will be multiplied by the probability P. Yeah. I also remember that in our last group meeting, there's one question about whether we can control which unit to present or not. Yeah, about this question, from my understanding, I think is actually we cannot control which specific neuron what is present or not. The thing we can control is the value of P. You can see that this one there's a high chance that this one can appear or not, but you cannot guarantee that which one to appear or not. Yeah. So, but I think the beauty of job out there is also in the random process, because for example, I have a network with with n neurons, and each neuron will appear with a probability of 0.5, right? But when we're training with a dropout, in this way, with the dropout, we can have a 2 to the exponential of n possible thinned network, because each neuron will appear with a probability of p. So we have this kind of, we have so many thinned neural networks, and during test, all of these small thinned network will cooperate with each other together to get a better performance. So that's, yeah. Then we have a parameter p, right? How we have to choose when we train it, when we train our network, we have to choose the value of p. Generally, the p is set to 0.5, but not for the input neuron. For the input neuron, the optimal p should be closer to 1 rather than 0.5. Yeah, generally, for me, I always choose 0.8. Yeah.
What type of data are you working with?
Data. I use because my previous I do human motion model. For me, the data is the joint data. Yeah, the XYZ value of each joint. Generally, is 17 joint of the human.
Okay.
Yeah.
So not very high dimensional.
No,
You
not
have
high.
17
Yeah.
variables to model.
Yeah. And the last one is last method I want to mention is the batch norm, which is a very powerful technique. The primary task of batch norm is actually to accelerate our training, to make your training faster. But in this paper, which proposed the job batch norm, they in their experiment, it reveals that it can also prevent overfitting, because when they removed in their network, they removed dropout and regularization, and only add the batch norm, and the accuracy doesn't change too much. So they said that batch norm also has can prevent overfitting. So this is the details of how to implement over batch norm. Is one during training, before you go to each nonlinear unit, before you go to the active function, it will normalize the data firstly. It will compute the mean value and variance of the input of each batch data, and then use the mean and variance to normalize the input, and then give them add the shift and the scale to get the normalize the final output. Final output will be the input of your active function, the active neuron. Yeah. This is for training. This is for training, but for test is different, because if during training, the value of this two, the mean value and the variance will keep updating during each iteration. But during test, it's different. Test, you will use the popular mean and variance. So you have to. So when you use batch norm, you have to specify whether it's training or not, because otherwise it will occur some strange, not error, but it will perform different when you do validation and when you do test. Yeah. That's for how to prevent the overfitting. I don't know. I just conclude these methods. I know. Do you have some other techniques?
I think pooling is used a lot in image architectures, specifically for images. So maybe I can talk about why I use.
Good.
So the other one pooling is. So let's say you have like let's say the resultant matrix in one of our layers, it's a 4x4 matrix. So there's so one of the kind of poolings you have is max pooling.
Mm.
So what it essentially does is it looks at a particular patch, right, and just picks out the max number. So in this case, it will reduce to like a 2x2 matrix. So today's patch max is 1, then 0. And so that the basic idea of pooling is that you want to identify where the feature is, but just whether the feature exists in that particular area. So, actually,
Even in the lectures that I think was in this week or next week's, Jeremy goes over why pooling is effective, right? He has a couple cases where he used a MNST data set in Excel. Was that in this lecture?
It's in lecture 4, I think.
Lecture.
I don't know what lecture.
Okay, yeah.
I read out some stuff yesterday. So it was mentioned last lecture that convolution was basically taking so that is like our image, right? Then the convolution in this our output. So what we think convolutions are is that you take element-wise multiplication and you sum up the values. Actually, this is mathematically correct. Yeah. So actually, it's the inverse. But then in neural network,
Transpose, right?
yeah, you transpose the kernel before you multiply. But in neural networks, what's typically implemented is not a full convolution, but what's called a correlation function. I think it is. And one thing I also wanted to talk about was what motivates the use of CNN. So like, why would you use a CNN over like a regular fully connected? Right. So there are 3 reasons according to Goodfellow. The first is sparse interactivity. The second is parameter sharing, and the third is variant representation. Okay, so the first sparse interactivity comes from the fact that we use very small kernels to do our computation. So instead of taking a very large input matrix and multiplying it by a very large output matrix, we do matrix multiplications that are very small. And this reduces the amount of memory you need as well as the amount of compute you do. Yeah. So this is good for parameter sharing is about the fact that in most fully connected layers, I mean, in a regular neural network, the parameters are only used once. While in the case of convolutional neural networks, you share them. So it also reduces memory usage. Yeah. And equivariant representation. This one I'm not super familiar, but I think the general idea is that something is equivariant when f of p of f is the same as g of f. Yeah. So the basic idea is that let's say the image is translated a little, and you perform the convolution, it's going to be the same as performing the convolution and then doing the translation. And this helps with in particular with things like time series data, where your features can just like shift around. But that one I'm still not very clear about. So actually, the chapter in Goodfellow's book is pretty short, and I think it's worth it.
Okay. Thank you. And
Thank you.
yeah, because overfitting is a very common problem for us. Yeah, when we train our network, it's very likely that your network is overfitting. But there's also another problem is underfitting. Yeah, but how do you define about how do you find that your network is underfitting? We have techniques for overfitting, yeah, because it's more common for our network. But for underfitting, how do you find out underfitting? Both on the training data and the test data, right? Yeah. Well, if your accuracy on both training and the test set is both of them are very low, it means that your neural network is underfitting. Another case is that your training loss is still goes down when your training stops, and your accuracy and still have the trend to go up. It means that your network doesn't train well, so you have to train more iterations. Yeah, that's all. That's for the train. It doesn't train well, but for other case, it still keep constant, and the accuracy is not that high. It is also underfitting. In this way, you have to add more hidden layers or add more neurons in each hidden layer. That's for underfitting. Yeah.
Okay, great. So let's all thank Li Chen.
Thank you.
And all of our moderators, Radhika, Jeffro, and everyone else for pitching in. So next week, you know who you are. So I invite you to stay around, maybe a little bit outside in the foyer area to discuss your duties for next week. Okay, so see you all, not next Friday, but the Monday after that, right? Okay, thank you. Have a good holiday.
Thank you.
Maybe later on you can send the slides to the Slack channel so that
Week 4.
your slides here, yeah, you can put it in the general channel just so that everyone who came to today's session can take them back. Okay.
Yes. When should I do the additions?
I will have to do some checking and I'll let you know this one. So just keep watching. Okay. Thank you.
I had a doubt regarding the lecture. Like in terms of the Fast.AI library, they have this parameter called pre-complete equal to this
True or false,
true or
yeah.
false, and they have a function for freezing as well.
Freezing
Aren't they doing the same thing?
No. There's a part where he talks about why pre-compute and freeze are not doing the same thing. So pre-compute, I think, just is speeding certain things up, but not allowing the layers to permute. Yeah.
I think it says the activations.
Correct.
But I'm not sure if freezing will do the same.
I'm not 100% sure because I haven't tried the experiments, but he did go into a little bit of detail why those two things are different. But if you guys remember, you can write it down. I mean, you can write it on general. Yeah, that would be good to raise up.